Okay, good morning. So, last class, I provide a brief introduction about the linear momentum equations. And the slide just summarize the items from the momentum equations. As you can see, follow the equation showing here. The left-hand side, the items is related to the net force, which is the sum of all the external force acting on the control volumes. And the right hand side there are two items. The first items we call that the momentum accumulations. As you can see, the items are associated with the momentum changes in the control volume with the time difference. And the second item we call that the net momentum flow, which is the momentum changes due to the outflow minus the momentum changes due to the inflow. And both two items are related to the control surface. And then the first line shows the general formula for the momentum equations. And just based on our problems, if the problem condition is under the uniform flow, and then we can replace the integration operator by the summation operators. Okay, so that's the two formulas related to the linear momentum equation. So the following slide, I would like to provide the physical interpretations about the momentum flow and the momentum accumulations. So we start from the momentum flow. As you can see, left hand side is the pipe flow, and we focus on the one cross section areas, and we just cut off the small piece of the pipe, and then we can very quickly to calculate the volume changes in the pipe, right? So we have the volume changes delta V will equal to the travel length L multiply the delta A, right? The delta A is the area of the pipe, and then we know that the delta the travel length L will equal to the travel velocities multiply the time intervals and multiply the delta A. So it is our delta V, the volume changes in the pipe and along the control surface, and we have the delta V, and then the delta V multiply the density. We have the mass, and the mass multiply additional velocity factors. We will have the momentum. So we just put the delta V inside the formula shown here. So we have the velocity delta T times, and the delta A multiply the density, and then multiply the velocity factor. But this equation, we only focus on one particle only, right? But in real case, we have many fluid particles, so we need to sum of the all of the particle cross the control surface. So we need to summations of along the control surface, and we have the density V delta T delta A, and multiply the velocity factors. Okay, and then we can calculate the momentum change along the control surface, so we can divide the equations with the time interval, right? With the time interval. So you can cancel out the delta t. So finally you only have the control surface at the rho v delta a multiply the velocity. Okay, and then if your cross-section area is quite smaller, so you can replace the sigma by the integration operator in here. So that's the momentum flow contribute the momentum changes along the control surface, and it's the physical interpretation. Okay, and then this is just one example to highlight the momentum flow. So as we can see, we have the fluid jet. So the line showing here, the yellow line showing here, we call that is the fluid jet. And then we have the vents in here. So we have the fan in here. So the blue line is the fan. So usually what's our problem? Our problem is how large forces required to hold the fan stationary. So how large the force required to hold the fan stationary. So if we have the conditions showing here, we know that the inflow v velocity and the inflow rate, mass flow rate, and this is the outflow velocity and the outflow the mass flow rate. And as you can see, they are the same. No matter is the inflow or outflow, the velocity and the mass flow are the same. So I first introduce why they are the same, because we have the continuity equation, right? And we know that the rho a1 v1 will equal to the rho a2 v2, and the a1 cross-section area multiplied the velocity 1 will equal to the a2 multiplied the velocity 2. So the a1 is our a1 v1 is our inflow in here, and the a2 v2 is our outflow. And then we have the Bernoulli equation. So we know that the P1 plus the gamma Z1 plus the 2 over rho V1 squared will equal to the P2 plus the gamma D2 plus the 2 over rho V2 squared. As we know that the P1 will equal to the P2 because they are exposed on atmospheres. So the gauge pressure of the P1, P2 are equal to 0. And we neglect the elevation difference between the 1 and 2. So we don't have the significant elevation difference, so we can cancel out the elevation items related to the Bernoulli equations. So finally, if the flow is an incompressible flow, so we can conclude that the V1 will equal to the V2 based on the Bernoulli equations. And then we put the idea back to the continuity equation, and then we can conclude that the A1 will equal to A2. So that's why the momentum flow, the figure showing here, they have the same velocities. and the same mass flow rate. Okay, and so now we are looking for the momentum equation applications. So for these questions, we know that we need to require some external force. So because maybe the momentum flow are not balanced. So we first consider the questions along the x directions. So what do we have? We have the mass flow out. In here we have the mass flow, the momentum flow due to the outflow, and we need to project the velocity vector into the x directions. So we have the out flow rate for the V2, and we project into the x directions. This is related to the outflow momentum changes, and we need to minus the inflow rate. So we have the mass flow and minus the inflow rate. So we can calculate, we put the number inside. So the mass flow rate is 2 kilograms per second. Multiply the V2 velocity is 8 meters per second. And multiply the cosine 45 degrees and minus the 2 kilograms per second. Multiply the V1 is also the 8 meters per second. So you can see that use your calculator to compute the answer. So the cosine 45 degrees minus 1 and multiply the 16. So that the answer will equal to the minus 4.68 Newton. Okay, so we know that the x along the x direction we have the external force. So we have the Vx along the x directions is equal to the 4.68 Newton, and the directions go to left. So the next we focus on the y directions for this question. So we have the y directions. So for the y directions, we only have the outflow contributions because the inflow only along the x direction. And so we have again we have the mass flow rate multiply the v velocity outflow, but I need to project to the y, and right now the velocity direction is downward, so we need to use the minus the velocity 2, and project to the y direction. We use the sine 45 degrees. So we can put the number inside. It's 2 kilograms per second. Multiply the minus the 8 meters per second and the sine 45 degrees. So the answer will equal to the minus 11.3 Newton. So we know that for our questions, we have additional force along the y directions is downward, and this is the Fy will equal to the 11.3 Newton. So we go back to see what's our questions. Our question is how large force required to hold the fan stationary. So we can, based on the momentum balance along the momentum flow along the control surface, and we can calculate the external force related to the Fx and Fy are the force that required to hold the fan stationary. Okay, so the next one, the slide we just introduced the momentum accumulation problems. As you can see, there are some questions listed in here. The first one, water flowing through the nozzle, and is the momentum of the matter inside the control volume changes with the time? If it is a change, so please answer this change is significant or not. So that's we know that based on the continuity equation, the mass inside the pipe are satisfied the mass conservation, so the mass didn't change. If the mass didn't change in the control volumes based on the continuity equations, and the second, we need to consider the velocity, the changes of the magnitude of the flow velocity. If the changes of the flow velocity also smaller, and small enough to neglect the changes of the velocity, and then we can calculate the accumulation items of the momentum can be neglected. So most of the problems, the momentum accumulation can be neglected. We can assume the momentum accumulation are always zero for our problem. Okay, so that's usually we discuss the problems we only have the external force well related to the momentum flow rate, and we will neglect the items for the accumulation momentum. So the table just a very quick summary the linear momentum equations and with the integrations formula and the sigma formula. Only one difference is the uniform flow or non-uniform flow. If the problem is under non-uniform flow, so we need to use the integrations to solve the problem. If the question is under the uniform flow, and then we can use the sigma deal with the problem. So I just highlight, as I mentioned before, the capital velocity v in here are different to the small velocity outside in here. So the capital is the velocity related to the control surface, and the small v is related to the selected the reference frame. So when we move to the topic related to the moving control volumes, and then we will discuss more details about how different they are, and how can we, when the control volume is moving, how can we deal with the problem. Okay, so here just show outline how can we deal the problem. So the first one, we need to sketch the force and the momentum diagram each other. And then because the force and momentum are factors, so we need to convert the factors to the scalar, especially for the x and the y directions individually. So actually we only have the two steps. The first one we just plot the force and the momentum diagrams, and the second ones we project the factor into the scalar equations, especially for the x and y or z directions. Okay. So let's just the momentum equations highlight. So for the pipe, this is the bent pipe for the nozzle problems. For the nozzle, so the exercise example showing here is a nozzle problem. For the nozzle, actually we have the weight of the water, right? And the second, we have inner pressures, because the cross-section area in here is inside the pipe. So we will have the pressure inside, right? And then we will have additional Fx and the Fy, which is the force required to holding the nozzle stationary. Because if you don't have the Fx and Fy, the nozzle includes the fluid flow, and the nozzle will move in, right? So you need to require additional force to hold the nozzle stationary. So this is a left hand side. We call that, we summarize all of the force in diagrams, and will equal to the momentum flow net rate are summarized in the right hand side. We call that the momentum diagram. So as you can see, what we have the velocity inflows along these directions, right? And there are some outflow. So in that the problem, we can after we plot the force and the momentum diagram, we can project the factor into each component to discuss the balance of the external force and the net momentum flow. So for the x directions, we have the Fx in here, okay? And the Fx will equal to the right hand side, the momentum already contributed the outflow can project into the x directions. So we have a mass rate multiply the V2 factor and project into the x directions. And this is related to the outflow, so the positive momentum change. And then we consider the y directions, okay? And there are many forces related to the y, because we have the Fy positive, and we minus the weight is downward, and the pressure is upward. P1 multiplied by A1 will equal to the momentum changes contributed by the outflow. So it is the m rate V2 and the sine theta minus the inflow rate, and the inflow is also upward directions. So the mass rate multiplied by V1. So that's the two scalar equations we discussed with the sigma external force summations is equal to the net momentum flow change into the different component. Okay, so that's the slide just summarizes the skill. How can we apply the momentum equation to the problem? So the first one, just select the the linear momentum equation when the problem involves the force and the accelerating fluid particle. That indicates that the sum of these external forces are not equal to 0. And the second, just plot the force diagram and the momentum diagram. And you just try to convert the factor into the scalar, and finally you can validate your answers. Okay, so usually we base in the following exercise, we always consider the accumulation items of the momentum is 0, and then we just discuss some of the force will be balanced by the momentum flow out minus the momentum flow in. Okay, so the table just summarize all of the problems we are looking for, and we can apply the momentum equation. So the problems can simply divide it into the problem when the control volumes is the stationaries and the control volume is the movings. So in class today, we only focus on the stationary control volumes problems. And then if the stationary control volumes condition is satisfied, and then there are three famous problems. The first is related to the jet and the fans, and the second related to the nozzle and the pipe bands. So how different when we discuss the problem related to the nozzle and the pipe bands, and then we will have the inner pressures. And for the pipe band, we have the inner pressure both two sides. But if we focus on the problem related to the jet and fans, they expose on the atmosphere, so the gauge pressure is 0. So we don't need to consider the inner pressure. And most of our problem, we require to answer how large the force to hold the device. That's how can we hold the jet and the fans problems, and how can we hold on the nozzle and the pipe band on stationary. And usually we consider the flow condition is uniform flow. Okay, so the final items in here, we will discuss when the flow is non-uniform flow. So that's the final exercise we will discuss. If our flow is non-uniform flow, how can we deal with the problem by applying the momentum equation? So that's the exercise showing here how large tension force required to hold the car. So we know that the tension force may have the hold the car with this direction to the left, and then we know that we have the V jet, right? We have the V jet, fluid jet, to the flow out to the left hand side, and actually we will have the weight for these problems, and maybe we have some frictional force and related to the car. So we have the frictional force. Okay, and the frictional force will proportional to a normal force. So we may have a normal force N. Okay, so you just consider all of the force, so we can draw the force diagrams, and will equal to the net of momentum flow. And in these questions, we only have the momentum rate flow related to the flow out. So we don't have the items in the for the inflow. Okay, so you can make a very quick balance between the force project into the x and the y directions, and we have the momentum out, and we can project the momentum into the x directions and also the y directions. Okay. So let's we do our first example related to the rocket, and that's a very famous exercise related to the model rocket behavior. So we just write down what we have the information from the questions. So the first one, we have the rocket mass. So we know that the rocket mass is 40 g, so it's equal to 0.04 kilogram. And then the house jet from the rocket motor has a diameter d is equal to 1 centimeter. So we have the diameter is 0.01 meter, and with the its host speed is the 450 meter per second, and we know that the gas have the density is equal to 0.5 kilogram per meter cubic, and assume the pressures in its host jet equal to the ambient pressure, so there is no gauge pressure. So please find the force Fs acting on the support that holds the rocket stationary. So if we go back to see our problem, because we have its host gas thrust out, and then the rocket would like to move up, going upward, right? So the support the support device will hold on the rocket stationary. So we just overcome the upward force to have the downward force. So we have a downward force is acting on the rocket to hold on the rocket stationary. So here just draw the force diagram, right? And right hand side is the momentum diagrams. So we can make the balance, and in this questions only include the momentum flow out. So we just consider the y directions. What we have? We have the force related to the weight, and the weight is downward, so we use the minus weight and the minus Fr acting on the control volume, right? And will equal to the mass flow out, but the velocity v is downward, so we use the minus mass rate multiply the velocity. So we just reorganize the equation. So the mv will equal to the w plus the fr, and the fr will equal to the mass flow rate v minus the weight. So this is our equations. So we need to find out what is the mass rate, right? So the mass rate will equal to the density multiply the discharge, and the discharge is equal to the velocity v and multiply the cross-section area A. So we have a density 0.5 kilogram per meter cubic, and the velocity is 450 meter per second. And the area, we only have the diameter, so the area equal to 4 over pi 0.01 square. So this is the unit equal to the meter square. So you can use the calculator to compute the answer. 0.5 multiplied 450 multiplied pi divided the 4 multiplied 0.01 second times. So that the mass flow rate is equal to the 0.0166767 the kilogram per second. And how about the weight? The weight is equal to the mass multiplied the g, right? So the mass is 0.04 kilogram, and the g is 9.81 meter per second square. So you can use your calculator to calculate the weight. It's equal to the 0.3924 Newton. Okay, so we have the mass rate and the weight, so we can go back to the formula. Fr will equal to the mass flow rate 0.01767 kilogram per second multiply the velocity is 450 meter per second, and minus the 0.3924 Newton. So you can use your calculator to compute the answer. The answer is equal to the 7.56 Newton. So we know that the Fr, initially we consider the Fr is downward. So we know that the Fr is the minus 7.56 newtons. But the question is required to answer the force is the Fs acting on the support that hold on the rock stationary. So we have the what is the Fs? The Fs we base on the Newton's third law. So the Fs is the reaction force of the Fr. So we have a reaction force along these directions, and we know that that is the 7.56 Newton upward. Okay, and usually the mass flow rate multiply the velocity. For the rocket we call that is the thrust force. The thrust force. So this is a very famous exercise. We are discussed with the rocket behaviors based on the modeling test. And the second exercise is related to the fluid jet. As you can see showing here, and the fluid right now is a concrete flow. And we only have the inflow for our problem. Okay, and we have the concrete density is equal to the 150 the bomb mass divided the ft cubic, and the area is the 1 ft square, and the speed is the 10 ft per second. And we know that the total weight of the car and plus the concrete is the 800 the pound force. So please determine the tensions in cable and the weight recorded by the scale. And we assume the flow is steady flow. And for this problem, actually the momentum accumulation is non-zero because the concrete jet provide the concrete mass into the control volume. However, we assume to be very small and was neglected. Okay? So again, we have the force diagram in here, and the right hand side is the momentum diagram. Okay, and we just consider we have the two directions along the x and another along the z directions. Okay, so first we focus on the x directions. So we have the minus tension, right? The x direction, the minus tension because the tension force is leftward, and we only have the inflow. So the inflow, we have the minus mass rate, and the velocity project into the cosine. Project to the x direction, we need to multiply the cosine 60 degrees, and the velocity is the positive directions to the x. Okay, so we know that the tension force directly equal to the mass flow rate multiply the velocity and the cosine 60 degrees. So what is the mass flow? Again, we need to calculate that the mass flow will equal to the density multiply the area and the velocity. So the mass flow rate is the 150 pound mass divided ft cubic, and the area is the 1 ft square, and the velocity is 10 ft per second. So you can see that is equal to the 1500 and the pound mass divided the second. Okay, so we know that the T will equal to the 1500 pound mass per second, and the velocity is 10 ft per second cosine 60 degrees. So that will equal to the 1500 and the pound mass multiply the ft dot the cosine 60 degrees, and the unit is the pound mass multiply the ft per second square. So we need to convert the unit showing here to be the pound force, right? So we need to divide it, the answer in here by the 32.17 to convert the unit to be the pound force. So I use the calculator to calculate the final answer. Cosine 60 degrees divided 32.17. So that will equal to 233.1 pound force. So, and this is the pound, and the answer is with the leftward. Directly go to left for the tension force. So the second, we focus on the vertical directions because we need to answer the weight recorded by the scale. So along the z directions, we have the minus weight plus the Newton, and because this is the inflow, so we have a minus the mass flow rate, and we project the inflow into the vertical direction, so the velocity to be the minus because the velocity is downward, right? So the velocity is downward, and we have the v and project into the z direction, so sine 60 degree. Okay, so the Newton n, the weight, will equal to the mass rate v sine 60 degree plus the weight. Okay, so we put the number inside. The mass is the 1500 pound mass per second, and the velocity is the 10 ft per second. Multiply the sine 60 degree, and we convert into the pound force, so divided the 32.17 to be the pound force, and plus the weight is the 800 pound force. So you can use your calculator to check the answer. I check by my calculator. So the answer is equal to the 1204 pound force, and this is the positive directions, so it's upward. So you just initially you consider the force directions, and then you will have the answer, right? And based on the answer, you can determine the directions of the force. So this is a second exercise. We apply the momentum equation to the fluid jet, and in that case, we only have the inflow contributed by the concrete flow. But because the concrete flow have this direction, so the car will move into the right? But we need to use the line to hold on the car. So we have the tension force to hold the car. And because you have put the concrete flow, and then so you have the additional weight increase caused by the concrete flow. So let the slide just conclude that the weight recorded by the scale is larger than the weight of the car because the momentum carried by the fluid jet. Okay, so we may have a 10 minutes break, and after the 10 minutes we back the class. See you then.